There is a surprising amount of probability in the glass bridge game of Squid Games. The objective of the game is to go through a set of tiles to get to the end platform. The catch is that one tile in each set will break if a person steps on it. The actual game has 18 sets of tiles, but for our purposes, I'm just going to show you an instance where there's 3 tiles. It's pretty straightforward to calculate the probability of one player winning, but when you start to add more players, it gets interesting. Just like the show, I'm going to assume the players have to cross the bridge at a specific order. Unlike the show, I'm going to assume that the players have perfect memory and no player tries any funny business. Most people know that going later has an advantage. I'm going to try to exactly quantify that advantage. We can perform this analysis elegantly using random variables. If you don't know what they are, just stick around for the cool graph, and if you do know what they are, sorry if I resurface any bad memories. We'll start off by defining a random variable xi that takes on the value of the number of new tiles that player I stepped on. The distinction of new tiles is very important here. Note that the new tiles can either be tempered or the regular ones. To demonstrate an example, suppose player 1 goes on the first set of tiles and picks the bad one and dies. Here x1 would take on the value of 1. Player 2 now knows which tile from the first step to set on. Let's assume that he gets lucky and guesses the next 2 correctly as well, and makes the end platform. x2 will take on the value of 2. Using his perfect memory, player 3 will follow the same sequence as player 2 and land on the end platform. However, because player 3 did not step on any new platform, x3 will take on the value of 0. Let p be the probability of picking the good tile from a set, and let q be the probability of picking a bad one. The event that player I steps on exactly k new tiles occurs when they step on k-1 correct tiles, and the kth tile they step on is incorrect. The probability of this event shown here is a geometric random variable. The key insight here is that the xi's for each player are identically distributed. Now there's a small caveat with there being a limited number of tiles in the game, but it doesn't change any of the intuition or the analysis of the math. Let SI denote the total number of new tiles all players up until now, including player XI, have stepped on. Now the elegance of this expression is that player I survives if and only if SI is greater than the total sets of tiles, which in the show was 18. If you think about it, this intuition makes sense, but it's important to remember that this doesn't tell us anything about the players that went before. All it tells us is that player I survived. Luckily, there's resources online that tell us how to calculate the probability of S taking on a certain value, which I've copied over here for clarity. Using this expression with some simple probability rules, we can easily calculate the probability that player I survives. I skipped a lot of steps, but this is what it should simplify to. From all the research that I could do, I couldn't find any other closed-form formula for the cumulative distribution function of a sum of geometric random variables, so this is as simple as I can get it. I've coded this exact formula in Python and generated a plot. The x-axis is the order of the player, and the y-axis is the probability of that player's survival. As you can see, most of the earlier players were pretty screwed, but later on, especially towards the middle, it jumped up significantly. Props to the writers for the design of this game.